What's up, guys? I'm Michael and welcome to my YouTube channel. Today we're going to talk about lists, iterators, and abstract data types. And what do I mean by list, iterators, and abstract data types? Well, first of all, remember, well, what exactly are iterators? So I showed you that other code before in one of the exercises of how to traverse through an an array or a vector or whatever. And one of the ways to do it is to use having an index starting at 0 and going up to the length of the array or the size or whatever thing it is. But what if you don't have an index? What if you can't traverse through an index? Well, you like that other data structure I told you in the exercises was a map where each one of them has like a specific value corresponds to a specific uh index. Instead of having an index like for a number as your index, they have like a specific value as that index. Well, what if you want to traverse through a map? Well, you can't do it with just an index I starting from 0 to the length of the array, because a map doesn't start at I equals 0. I mean, it can, but most maps, they're generally not numbers to numbers, but they're actually a corresponding certain value that is not a number, and it maps to another number, right? That's what mostly maps are. Or even like a linked list. So you can't really traverse a linked list with just having an index, right? So that's why we have something called iterators. So we're going to go over lists, iterators, and abstract data types. So we're first going to go over vectors. We'll go over lists. And we're going to go over sequences. And we'll have a case study on bubble sort, all right? So what are vectors? Well, we talked about vectors already. So let's say we have a collection of S of n elements stored in a certain linear order so that they can refer to the elements in S as first, second, third, so on. Such a collection is as a list or a sequence, and you can uniquely refer to each element E in S using an integer in the range 0 to n minus 1. So we already used this vector before, and a vector is basically just an array, except you could like resize its stuff. It's like a list of things, right? And it has the index of an element. E in S is the number of elements that are before E in S, right? Yeah, the index of whatever it is. Hence, the first element in S has an index of 0. The last element has n minus 1. Also, if an element of S has index I as its previous element, has an index I minus 1, and its next element, if it exists, has index I plus 1. This concept of index is related to that of a rank of an element in a list, which usually are defined to be one or more than its index. So the first element is at rank 1 and rank 2 and so on. So a sequence that supports an access to its elements by the indices are called vectors, and these are basically they're basically a better way to use better way of having a collection of things, of numbers and stuff, better than an array, because you could resize them basically. That's a good thing about vectors. Since our index definition is more consistent but with the way arrays are indexed in C++ and other common programming languages, we refer to the place where an element is stored in a vector as its index rather than its rank, okay? The concept of index is simply a powerful notion, since it can be used to specify which to insert a new element in our list and where to remove an old element. So here's the vector abstract data type. A vector, which is called an array list, I think, yeah, which is also called an array list, is an abstract data type that supports the following fundamental functions in addition to the standard size and the empty functions. In all cases, the index parameter I is assumed to be in the range 0, less than or equal to size minus 1, right? And okay, so these are the functions for a vector. At returns the element of V with the index I, which is an error condition. An error condition occurs if I is out of range, right? Set I at E replaces the element at index I with E. An error occurs if I is out of range. Insert IE inserts a new element E into V to have an index I. If an error occurs if it is out of range. So yeah. Erase I removes v from the element at index I, and an error occurs if I is out of range. Yeah. So these are the things for all the methods of a vector, and what's good about them is that you could insert and delete things in a vector that you can't really do in an array. So the good thing about vectors is that you could insert at an element something at an index, right? You could erase it as at a certain index. You could set it at a certain index, and you could get the element at a certain index, right? So we do not insist that an array be used to implement a vector, so that the element at index I is stored at index I in the array. Although that is one very natural possibility, the index definition offers us a way to refer to the place where an element is stored in a sequence without having to worry about the exact implementation of that sequence. The index of an element may change when the sequence is updated. However, as we illustrate in the following example. So they're just saying that they might not use an array to implement a vector. But a vector is basically a better version of an array in that you could insert and delete at a certain index. Okay. Alright, so let's go to the next page. Here's an example where they have a certain operation on an empty vector v. So let's say you insert at index 0, 7. Well, 7 is going to get inserted at the index 0. If you want to insert a value at 0, 4, well, 4 is now going to have the value at index 0, and 7 gets pushed over, right, to the right. If you want the value at 1, well, the value at 1, 0, 1 is 7. If you want a value at insert at 2, 2, well, that's just 2 because they insert it at the element 2, 2, right? If you want the value at 3, it gives an error because there's no value at element 3. 0, 1, 2, 3, there's no error. If you want to erase at element at 1, 0, 1, well, yeah, it's going to erase the 0, 1, which is 7. It's going to erase the 7. If you want to insert an element at 1, 5, which is insert at index 1, the element 5, well, it's going to insert 5 in that element, and so on and so forth, yeah. If you want to set a certain element at, it's going 3 to have 8, 0, 1, 2, 3, this replaces the 2 to have value 8. Okay, so a way to implement this is to use an array, and it's not really recommended to do it using an array, mainly because the problem about arrays is that you can't really resize them. If they go past the length, then you have to copy everything over. So I'll just show you how they want us to implement an array-based implementation. So an obvious choice for implementing the vector is to use a fixed size array A, where A of I stores the element at index I. They chose the size n of an array to be sufficiently large and to maintain the number n is less than the n a number of elements in the vector in a member variable. The details of implementation of the functions of the vector abstract data type are reasonably simple. To implement the at operation, for example, you just return it, right? Inserting and erasing is harder because, I mean, let's face it, you gotta shift everything over, right? Or resize it. That's the problem with arrays. So to insert, they're gonna loop through the whole array. They're gonna loop through the whole array, starting at the last element, and they're gonna copy everything over. Yeah, they're gonna copy everything over, and then they insert the element at whatever you want to insert at. So like, I could explain it, but I guess there's so like, okay, let's say I want to insert let's say I have an array at 3 where's 3, yeah, 3 1 4 or something, I don't know, and this is the index 0 1 2. If I want to insert something at index, whoops, stop, my bad, we'll insert something at index 1. Well, let's think about this. Well, if I want to insert at index 1 the value 5, right? So the cursor's not showing. So at index 1, the value 5. Right, whoops. I didn't mean to do that. So I want to insert at 1, 5, right? Well, how would I do that? Well, what they're doing is they're going to loop through from there's they're gonna loop through from n minus 1 down to I, right? So they're gonna copy everything over. So then that basically says, okay, so I'm gonna insert from n minus 1, right, down to I. So what is I currently? I want to insert at the element I, right? At element 1, right? And I want to insert the value of 5. So I'm going to loop through from n minus 1. And what is n? There's three elements currently. So I'm going to loop through from 2. Okay? So what am I going to do? So j is going to start from n minus 1, which is 2. So j is going to start from 2, right? Because there's 3 elements and then you n minus 2. I'm going to copy everything from j plus 1 is going to equal to j, a at j. So j plus 1, a at 3. Wait, hold up. Where's my, oh yeah. A at 3. So a at 3. We're assuming this array is really large. So we're assuming it has way more values. Okay, I'm going to copy thing at j at 3. So j at 3 is going to have the value of j at j at 1. Oh no, j at 2. J at 2. My fault. So j at 3 is going to have the value j at 4. So it's going to have j at 2, which is going to have 4, right? And then j is going to get subtracted. So it's out j at 1, right? Then a at j plus 1, which is 2. A at 2 is going to have the value a at j. So that's going to be 1. And then they're going to, after that, this loop terminates because we hit the value of I, right? Because I was 1, right? So now at that moment, a at I, so a at 1 is going to have, we insert the value that we want to have, which is 5. At 1, we're going to have the value, we're going to insert at 5. And then we increment the size n equals n plus 1, which is, that's what they do here. So size gets added 1, so that has a size 4 now. So here they're assuming that the array is very large to do it, and that they're not resizing it. But yeah, erasing it is about the same. You're copying everything over. So let's just do that right now. So how are they going to do this? So here, I'm going to delete this, and I'm going to delete this, and I'm going to delete this. Okay. So if I want to erase something, whoa, my fault. Okay, so let's say I have an array of 1, 2, and 3, right? If I want to erase the value at index 1, so I'm going to erase it at index 1. So I is equal to 1. I is equal to 1, right? So what they're going to do, they're going to loop from I plus 1. So j is going to have, my fault. Completely my fault. I pressed the wrong button. Let me just go back. Alright, right here. So j is going to have I plus 1. And what is that? I plus 1, which is 2. So j is going to start from 2. And I'm trying to erase the value at 1, right? I'm trying to erase this number. I'm erasing this, right? So we're going to start from j is going to equal to I plus 1, which is I is 1, so j is going to be 2. And we're going to loop through from a at j minus 1. So what's j minus 1? 2 minus 1 is 1. So a at 1 is going to now have a at j. What is a at j? Well, j is 2. So a at 1 is going to have the value of 2. So this, a at 2. So this, what's a at 2? A at 2 is 3. So a at 1 is going to have the value of 3. So this is going to have the value 3. Then j minus, j becomes 1, and I equals to j, so they stop this loop, and then we decrement the size to have 1 less. So size now going to equal to 1 less. And then because size is 1 less, this is originally there were 3 elements. It's going to have 2. So when you loop through it, it's just going to ignore it, even though this element still exists. All right, it's just going to ignore it because when you loop through the size, because size is 1 less, Even though the number is still there in memory, the size is just when you loop through it, you loop through the size because it's one less. The last value would be 1. We'll add index 1. That's why. All right, that was insert. The methods insert and erase in the array implementation of vector ADT. All right, the member variable n stores the number of elements. An important and time-consuming part of the implementation involves the shifting elements up and down to keep the occupied cells in the array contiguous. Yeah, that's the problem, shifting it down. So these operations are required to maintain our rule of always storing an element whose index at index I of array A. Yeah, so the problem is about shifting it up and down. So that's the main problem. Let's see. Performance of a simple array-based implementation. So here the table shows the worst case running time of the functions of a vector with n elements realized by means of an array. The methods empty, size, at, and set clearly run in O of 1 time, but the insertion and removal functions can take much longer than this. So in particular, when you insert at a certain number, it runs in O of n time. The worst case for this operation occurs when I is equal to 0, since all the existing I elements have to be shifted forward. A similar argument applies to the function erase at I, which runs in O of n time, because we have to shift backward n minus 1 elements in the worst case scenario, which is I equals 0. In fact, assuming that each possible index is equally likely to be passed as an argument to these operations, the average running time is O of n because we have to shift n over 2 elements on average. So here's all the time complexities. O of n means you have to loop through the whole thing to insert, and yeah, everything else is constant because that just depends on the machine. Depending on performance of a vector with n elements realized by an array, this is space of O and n, where n is the size of array. Okay, looking more closely at insert and erase, we note that they each run in time O of n minus I plus 1. For only those elements at index I and n higher will have to go up or down. Thus, inserting or removing an item at the end of a vector using the functions insert and erase take O of 1 time respectively. Moreover, this observation has an interesting consequence for the adaptation of the vector ADT to the DQ ADT in the section. If the vector ADT in this case is implemented by means of an array, as described above, then the function insert back and erase back at the DQ can each run in O of 1 time. However, the function insert front and erase front at the DQ each time run in O of n time. Actually, with a little effort, we can produce a array-based implementation of the vector that achieves O of 1 time for insertion and removing at index 0, as well as inserting and removing at the end of the vector. Achieving this requires that we give up our role that an element at index I is stored in the array at index I. However, as well such, we can use a circular array approach like the one we use in the implementation to implement a queue, and we leave out the implementations as an exercise. Okay, so that's just what they're saying when you use an array to implement it. Yeah, or another data structure. Here, let me just go back up. I think I pressed the next one. My fault. Yeah, so let me just keep going next. I'm gonna go next. Okay. So, let's talk about an extendable array implementation. And this is another, I think it's the same thing. Pretty much. But a major weakness of the simple array implementation for the vector ADT given in this section is that it requires advanced specification of the fixed size capacity for the total number of elements that may be stored in the vector. But sometimes you actually don't know how much you want to store in your vector. So if the actual number of n elements is much smaller than n, then this implementation will waste space. Worse, if n increases past big N, then if small n goes past big N, then this implementation will crash. Fortunately, there is a simple way to fix this major drawback. So let us provide a means to grow the array A that stores the elements of a vector V. In C++ and in other programming languages, you can't actually grow the array A. Its capacity is fixed at some element n, as we have already observed. Instead, when overflow occurs, when the number of values is actually equal to the total capacity, the function insert is called. We perform the following steps. You allocate a completely big new array that's bigger, copy all the values over, then you deallocate the old one and assign the new array. That's what I did in one of the exercises where I showed you where I had to copy all the elements over and then reassign the array. This array replacement strategy is known as Extendable Array, and it can be viewed as extending the endpoint of the underlying array to make room for more elements. The strategy is much like the hermit crab, which moves into a larger shell when it outgrows its previous one. So, given the implementation of the abstract data type using an extendable array in the code fragment, to avoid the complexities of templated class, they have adopted the earlier practice of using a type definition to specify the base element type, which is an int in the case. The element is called array vector, and they leave the thing to be implemented generically as a class. So here are the steps for growing an extendable array. Create a new array, copy all the elements over, reassign it. The class definition is different from the operations given in the abstract data type. For example, you could provide two means for accessing individual elements of the vector. First involves overriding the C++ array index, which you have to override the operator brackets, and the second is the at function. The two functions behave the same, except that the at function performs a range test before each access. Note that the similarity with the STL vector class is given. If the index I is not in bounds, this function throws an exception. Because both of these access operations return in a reference, there's no need to explicitly define a set function. Okay, so instead we can simply use the assignment operator. So yeah, the ADT function v.set could be implemented either as a vi at equal 5 or just v dot at I is equal to 5. So yeah, you could do that. So here are all the functions. You could have array vector, which is the name of we're implementing the vector with an array. This is a class. They have the constructor, the number of elements, checking if it's empty. We have a element at index operator, and we have an element at index I, which throws the index out of bounds if I is not the right I, like if it's out of bounds. You have an erase, which removes the element at index I. You have the insert, which inserts the element at index I, reserve, and yeah. The member data for class array vector consists of an array storage A, the correct number of n elements in the vector, and the correct storage capacity. The class array vector also provides the ADT functions insert and remove, which you discussed below. Wait, let me see, did I miss something? And they also add a new function called reserve that it's not part of the ADT. Function allows the user to explicitly request that the array be expanded for a capacity, okay, of at least n. Okay, so that's just increases the capacity. If the capacity is already larger than this, then the function does nothing. Okay, so even though they didn't bother to show them, the class also provides some of the standard housekeeping functions, and these consist of a copy constructor, an assignment operator, and a destructor. Because the class allocates memory, their inclusion is essential for the complete and robust class implementation. They also leave it as an exercise. Okay. Yeah. They present the class constructor and a number of simple member functions, When the vector is constructed, they don't allocate any storage and simply set A to null. Okay. Yeah, these are all the things. So set capacity, set n, set A to null for the constructor. Size returns n. Empty returns whether size is equal to 0. Index at element at index I just returns the element at it. Yeah, throw index out of bounds A at okay. So that's all they have. They also present a number of member function erase. As mentioned above, it removes an element at I by shifting all the elements from the last element down by one position. Yeah, that's what they do. Okay, so finally they also represent the reserve and insert functions. Here are the reserve and insert functions. Reserve just copies all they create a new allocate. Whoa. What did I just do there? Whoa. Wow, I went back way too much. Okay, so the reserve function basically copies if it's greater than the capacity, right? If the capacity is greater than or equal to n, they do nothing. Otherwise, because if that's the reason why they don't do anything is because, I mean, if you already have enough size, you don't have to do anything, right? You don't have to reserve anything. If your size is already fine, like you don't have to expand your array. That's why they don't do anything. But otherwise, they basically allocate new completely new array, and they copy all the elements over from I to n at A of I, and then if it's not null, they delete the old one, and then they set the new one to equal to that array. That's basically what they're doing. Insert is about the same. Oh yeah, they expand it first. We use the reserve to expand the array, and they copy everything over. Pretty much, yeah. Alright guys, we're back, and I just got a drink of water, and let's analyze the efficiency of this extendable array. In terms of efficiency, having this replacement strategy might seem slow, but after performing just one array replacement required by an element insertion, takes O of n, which is not very good. But after we perform an array replacement, our new array allows us to add more elements to the vector before the array must be replaced again. So the observation allows us to show that the running time of a series of operations performed on an initially empty vector is proportional to the total number of elements added. So for shorthand notice, let's refer to the insertion of elements to be in a vector as a push. Using a design pattern called amortization, we show below that performing a sequence of push operations on a vector implemented with an extendable array is quite efficient. So let V be a vector implemented by means of an extendable array. The total number of time to perform a series of n pushes, starting from n being empty, of having a size of n equals 1 is O of n. So to perform the analysis, they have a computer. View the computer as a coin operation of appliance that requires the payment of $1 cyber for a constant amount of computing time. When an operation is executed, you should have enough cyber dollars available in your current bank account to pay for that operation's running time. Thus, the total amount of cyber dollars spent for any computation is proportional to the total time spent on that computation. So the beauty of using this analysis method is that we can overcharge some operations in order to save up cyber dollars to pay for the others. So assume that $1 cyber is enough to pay for the execution of each push operation in V, excluding the time spent for growing the array. Also, let us assume that growing the array from size k to size 2k requires k cyber for the time spent copying the elements. So if you charge each push operation 3 cyber and then overcharge each push operation that does not cause an overflow by 2 cyber, think of the 2 cyber profited in an insertion that does not grow the array as being stored in the elements inserted. So the overflow occurs when a vector has 2 to the I elements for some I is greater than 0. The size of the array used by V is 2 to the I. Thus doubling the size of the array requires 2 to the I cyber. Fortunately, these cyber can be found at the elements stored in cells 2 to the I minus 1 through 2 to the I minus 1. Suppose that the previous overflow occurred when the number of elements become larger than 2 to the I minus 1 for the first time, and thus the cyber stored 2 to the I minus 1 through 2 to the I minus 1 were not previously spent. Thus, we have a valid amortization scheme in which each operation is charged $3 and the computing time is paid for. So if you paid the execution of n push operations using 3n cyber. So you can see here a series of push operations on a vector. An 8-cell array is full with 2 cyber stored at cells 4 through 7. A push operation causes an overflow and a doubling of capacity. Copying the 8 old elements to the new array is paid for by the cyber already stored in the table. Inserting the new element is paid for by one of the cyber charged to the push operations, and 2 cyber profited at storage cell 8. Let's talk about STL's vectors. So we introduced the STL class for the vector, as we mentioned before, and they're like standard arrays in C++, but they're superior. Basically, I just told you that you could add elements to it, you could resize it. That's a good thing about STL, okay? So provided it provides you a bunch of built-in classes and algorithms. Classes provided by STL are organized in various groups. Among the most important of these groups is a set of classes called container. A container is a data structure that stores a collection of objects. Many of the data structures that study in this book, known as stacks, queues, lists, are examples of STL containers. The class vector is perhaps the most basic example of an STL container class. We discuss containers further in the section, but the definition of a class vector is given in the system file include file vector. The vector class is part of the std namespace, so it is necessary either to use std vector or to provide an appropriate using statement. The vector class is templated with the class of the individual elements. For example, the code fragment below declares a vector containing 100 integers. So if you declare it declares a vector of 100 integers. We refer to the type of individual elements as the vector's base type. Each element is initialized to the base type's default value, which for integers is 0. So this basically is like declaring an array of size 100, except it's a resizable array vector. STL vectors behave in many respects like standard C++ arrays, but they provide many different additional features. As with arrays, individual elements of a vector object can be indexed using the index operator, which is a good part about STL. You could use index operators. Elements can also be accessed by a member function called at it. The advantage of this member function over the index operator is that it performs range checking and generates an error exception if the index is out of bounds. So unlike C++ arrays, STL vectors can be dynamically resized, and new elements may be efficiently appended or removed from the end of the array. When an STL vector of class objects is destroyed, it automatically invokes the destructor for each of the elements. So with C++ arrays, it is the obligation of the programmer to do this explicitly. STL vectors provide a number of useful functions that operate on entirely vectors, not just individual elements. So this includes, for example, the ability to copy all or one part of one vector to another, and the ability to compare the contents of two arrays, and the ability to insert and erase multiple elements. Here are the principal member functions of the vector class. Let V be declared to be an STL vector of some base type, and let E denote a single object of this same base type. For example, V is a vector of integers and E is an integer. So vector N. Construct a vector with space for n elements. If no argument is given, create an empty vector. Yeah, this creates an empty vector. Size returns the number of elements of V. Empty checks if V is empty. Resizes it for the space to have n elements. Reserve requests that the allocated space be made larger to hold n elements. The operator, array operator, yeah, that just returns the index. At, same as the array operator, but throws out of range exception. Yeah, I'm guessing this is something that they added. I don't think it's in STL, but I don't know. Because STL, they don't throw out of bounds. Oh, no, they do. Yeah, they throw out of range exceptions. They don't throw index out of bounds, though. Front returns a reference to the first element. Back returns to the last element. Push back adds a copy to the end. Pop back removes the last element of V and reduces the size. So when the base type of an STL vector is a class, all copying elements, for example, in pushback is performed by invoking the class's copy constructor. Also, when elements are destroyed by invoking the destructor, the class's destructors are invoked on each deleted element. So STL vectors are expandable. When the current array space is exhausted, its storage size increases. Although we have not discussed here yet, the STL vector also supports functions for inserting elements at arbitrary positions, and we already said that. All those methods we said before. Yeah. There are differences between our array vector class and STL vector class. One difference is that STL vec constructor allows for an arbitrary number of initial elements, whereas, okay, so the one that we created, we cannot have initialized an arbitrary number of elements. I guess we could do that. I don't know. So, the STL vectors dot front is equivalent to v of 0 and n minus 1, respectively, where n is equal to size. Okay. The STL vector functions push back and pop back are equivalent to our array insert and remove. Yeah, okay. Alright, let's talk about lists. Let me get another drink of water, and then I'll come back here and talk about lists. Alright guys, let's talk about lists. So, using an index is not the only means of referring to the place where an element appears on the list. If you have a list L implementing with a single linked list, then it could possibly be more natural and efficient to use a node instead of an index for identifying where to access and update a list. So in this section, we define the list ADT, which abstracts the concrete linked list data structure using relevant position that abstracts the notion of the place in the list. So let's talk about node-based operations and iterators. So let L be a singly or doubly linked list, and we would like to define functions for L that take nodes of the list as parameters and provide nodes as return types. Such functions could provide significant speedups over index-based functions because finding the index of an element in a linked list requires searching through the list, incrementing from beginning to end, and counting as many elements as you go. So if you want to define a hypothetical function remove that removes the element L at a node of a list, using a node as a parameter allows us to remove an element in O of 1 time by simply just removing it, right? And changing the previous and next of the neighbors. And in O of 1 time we could insert a new element E into L with an operation such as insert, which specifies the node V before which the node of the new element should be inserted. In this case, we simply link in the new node. Defining functions of a list ADT by adding such node based operations raises the issue of how much information we should be exposing about the implementation of the list. Certainly it is desirable for us to be able to use either a singly or double linked list without revealing the details to the user. Likewise, we do not wish to allow a user to modify the internal structure of a list without ever our knowledge. So the modifications would be possible if we provide a pointer to a node, right, that allows us to access the internal data in the node for previous and next. Now, to abstract this in different ways of storing elements in various implementation of lists, we could introduce a data type that abstracts the notion of a relative position in the place of an element within a list. So we're going to call this the position of an element in a list. And we want this object not only to access the individual elements of a list, but we also want to move around to, get all the elements of the list. We want to adopt the convention used in C++ template library. So we call it an iterator. All right. And let's talk. So what are containers and positions? So to expand our set of operations for lists, we abstract a notion called a position that allows us to enjoy the efficiency of a doubly linked list without violating object-oriented principles. So we think of the list as an instance of a more general class of objects called a container. And a container is a data structure that stores any collection of elements. And we can assume that the elements of a container can be arranged in a linear order. A position is defined to be an abstract data type that is associated with a particular container and which supports the following function. Element returns a reference to the element stored at this position. So C++ allows us to overload operators, provided us with a elegant alternative manner in which to express the element's operation. In particular, we could overload the dereference operator, and so that given a position, a variable p, the associated element can be accessed by star p rather than p.element. And this can be used for accessing and modifying the element's value. And a position is always defined in a relative manner, that is, in terms of its neighbors. Unless it is the first or last, a position q is always after the some position p and before some position r. And a position q is associated with some element e in a container that does not change even if the index of an e changes in the container unless we specifically remove e. So if the assigned node is removed, we say that q is invalidated. Moreover, the position q does not change even if we replace or swap the elements at q with another element. So the positions don't change themselves unless you delete something or insert something, right, at another place in the position. Positions don't change. Like it's at index 0, 1, 2, 3, 4, 5, 6, whatever. So that's what they're talking about here. So we could, there's something called iterators, right? And although a position is useful, it would be more useful to be able to navigate through the container or whatever, advance to the next position in the container. And this is called an iterator. An iterator is an extension of a position. It allows us to access the node's element, but also provides a way to navigate forwards and backwards through the container. And there are many number of ways which to define an ADT for an iterator object. For example, given an iterator object P, we could define an operation P.next, which returns an iterator that refers to the node just before P in the container. So because of C++ abilities to overload operators, there's a more elegant way to do this by overloading the increment operator ++. In addition, the operation ++ advances P to the next position of the container. By repeatedly applying this operation, we can step through all the elements of a container. And for some implementation of containers, such as a doubly linked list, navigation may be possible with both forwards and backwards. So if so, we can overload the decrement operator to move the iterator backwards in the container. In addition to navigating through the container, we need some way of initializing an iterator to the first node of the container and determining whether it has gone beyond the end of the container. To do this, we assume that each container provides two special iterator values, begin and end. The beginning iterator refers to the first position of the container. We think of the ending iterator as referring to an imaginary position that lies just after the last node of the container. Given in a container object L, the operation L.begin returns the instance to the beginning of the iterator, and the operation L.end returns the instance to the end of the iterator. So, just like our linked list, this time it's an iterator. Instead of doing .front and back or rear, whatever it was, I forgot, or .tail, I think. If you do L.begin, that's the, think of an iterator as like a pointer to whatever object at the front, right? So if you do L.begin, it returns whatever value at the front. And if you do L.end, it returns basically just after the last node of the container. Okay, yeah. So in order to, I don't know why do they define this like that, but whatever. They should have it point to the end, but it doesn't matter. In order to enumerate through all the elements of the container, we have to define iterator P initialized to P.begin, and you have to keep advancing it, right? The associated element is accessed using *P. Yeah, because we're thinking of that as a pointer, right? To access the data that this thing is pointing at, right? You can enumerate all the elements of the container by advancing P to the next node using ++P. We repeat this until P is equal to L.end, which means that we have gotten fully off to the end of the list. Alright, list, the abstract data type. Using the concept of an iterator to encapsulate the idea of a node in a list, we can define another type of sequence ADT called simply the list ADT, abstract data type. In addition to the above functions, we include the generic functions size and empty with the usual meanings. This ADT supports the following functions for a list L and an iterator P for this. So begin returns an iterator referring to the first element of the list, right? And same as end, if L is empty. End returns an iterator returning to an imaginary element just at the last of the end. And insert front allows you to insert to the front of the list. Insert back allows you to insert element E, whatever, E, when we took any number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, front, back to the last element of the list. Insert an element E into L just before the position P in L. So just before the number 2, it inserts at just before number 2. Erase front removes the front. Erase back removes the back. Erase P removes an element at a position. And now it invalidates P as a position. Alright, so we have functions insert front, insert back are provided as a kind of convenience since they are equivalent to insert L.begin, E, and insert L.end, E, respectively. Similarly, erase front and erase back can be formed by the more general function erase. So an error condition occurs if an invalid position is passed as an argument to one of the operations. Reasons for this could be like the position was never initialized, right? The position was previously removed from the list. The position resulted from a illegal operation, such as adding it p++ when it pointed to the end, right? You access beyond the position of the end. We did not check for the errors in our implementation. Instead, it is the responsibility of the programmer to ensure that only legal positions are used. We show a series of operations for an initially empty list, shown here below. If we use variables p and q to denote different positions, and we show the object currently stored at a position in parentheses in the column, the output column. Insert front 8 p equals beginning. Okay, yeah, inserts 8 p equals the beginning. So p points to the beginning now. Insert back inserts 5 at the back, so now it has 8 5. Q equals to p. Okay, so q points to where p was pointing, which is the beginning, and then q++. That's just going to print out 5. Yeah. Well, yeah, you add 1 to q, right? Yeah. It's going to point to 5. Yeah, that's where q is 5. P points to beginning. Okay, yeah. Does p equal the beginning? Yes. Yes. Yes, it does. Okay. It does. Insert q3. That's going to insert 3 at position q, which is the second element here. Right? Second element, because q++, q pointed to where p pointed at, and then you add 1, that's 5, right? Insert 3, it's going to insert at 3. Okay, star q equals to 7. That returns the data that it was pointing at. Insert front 9, inserts the value at the front. Erase back, erases the last element. Erase p, erases the position at p. Erase front, erases the front. List ADT with its built-in notion of position is useful in a number of settings. For example, a program that models several people playing a game of cards could model each person's hand as a list. Since most people like to keep cards of the same suit together, inserting and removing cards from a person's hand could be implemented using the functions of the list ADT, with the positions being determined by a natural ordering of the suits. Likewise, a simple text editor embeds the notion of the position, insertion, and removal, since each editors typically perform all updates relative to a cursor, which represents the current position in the list of characters of text being edited. Okay, so there's a couple of ways we could do this. We can make this iterator or our list. Most efficient way is to use a doubly linked list, because you have the header and the tail, right? Trailer, header, trailer, whatever. These are created when the list is first constructed. The other elements of the list are inserted between these sentinels. Following our usual practice, in order to keep the code simple, we sacrifice generality by foregoing the use of class templates. We provide a type definition element, which is the base element type of the list. So we leave the details of producing a fully generic template class as an exercise. Okay. For defining the list, we call a node list. We implement 2 important structures. The first represents a node of the list. The second represents an iterator for the list. Both these objects are defined as nested classes within node list. Since users of the class access nodes exclusively through iterators, the node is declared a private member of node list, and the iterator is just a public member. The node object is called a node and is presented in the code fragment 6.6 as a simple C++ structure which has only public data members consisting of the node's element, a link to the previous node of the list, and a link to the next node of the list. Since it is declared to be private to node list, its members are accessible only within node list. Okay, so that's that. Our iterator object is called the iterator. The users of class node list, it can be accessed by the qualified type name node list iterator. Its definition, which is presented in code fragment 6.7, is placed in the public part of node list. An element associated with the iterator can be accessed by overload dereferencing operator star. In order to make it possible to compare iterator objects, we overload the inequality operators. Okay, yeah. So to move forward and backward by providing the increment and decrementing operators. We declare node list to be a friend so that it may access private members of iterator. The private data members consist of pointer v to the associated node of the list. We also provide a private constructor which initializes the node pointer. The constructor is private so that node list is allowed us to create new iterators. Yeah. Class iterator realizes an iterator for a doubly linked list. Okay, so here they have the overload the star operator, reference to the element. Alright, overload equal to compare the positions. Overload not equals, yeah. Overload plus plus, move to next. Overload minus minus, go to the previous. Use a friend to give nodes list access to node, and this is where you create a node and stuff like that. We present the implementation of the member functions for the iterator class. These all follow directly from the definitions given earlier. So node list iterator. Node list iterator. Okay. That just looks funny. Okay. It's a constructor for the node. Okay. Yeah. You just set the node pointer to equal to it. Star operator just returns the element. Equal checks if the element is equal to each other, right? If the node points to each other. Okay. Yeah. Not equals checks if the thing is not equal. Yeah. Plus plus moves it to the next and returns the object that the pointer is pointing to, the current thing is pointing to. Minus minus goes to the previous and returns the data that this thing was pointing to. Yeah. To keep the code simple, we have not implemented any error checking. We assume that the functions of code are defined outside the class body. Because of this, we are referring to the nested iterator class. Iterator, we need to apply the scope resolution operator as a node list iterator, so the compiler knows that we are referring to the iterator type associated with node list. Observe that the increment and decrement operators not only update the position, but they also return a reference to the updated position. This makes it all possible to use the result of the increment operator as in q equals to plus plus p. Okay, so having defined the supporting structured node and iterator, let us now present the definition, declaration of node list, which gives in the code fragment. The class begin by inserting the node and iterator definitions from code fragment. This is followed by the public members that consist of a simple default constructor and members of the list ADT. We have omitted the standard housekeeping functions from our class definition. These include the class destructor, copy constructor, and assignment operator. The definitions of destructor is important since the class allocates memory, so it's necessary to delete this memory when an object of this type is destroyed. Okay. Whew, that was a lot. Okay, these are all the functions for the node list. Default constructor returns, we need the size, we need to check if it's empty. Begin, okay, that's the beginning position. End position, just beyond the last position. Insert the front, insert the back, insert E before P. Erase front, erase back, erase. Okay, yeah, remove P. Private is int and header, trailer. Okay. Private members include pointers to the head and tail sentinel nodes. In order to implement the function size efficiently, we also provide a variable n which stores the number of elements in the list. Next, let us see how the various functions of class node lists are implemented. We begin by presenting a number of simple functions, including constructor, size, and empty functions, and the begin and end functions. Class constructor creates an initially empty list by setting n to 0, then allocating the head and tail nodes and linking them together. The function begins returns the position of the first node of the list, which is the node just following the head sentinel. The function end returns the position of the trailer as desired. This is the position following the last element of the list. In both cases, we are invoking the private constructor declared within the class iterator, and we are allowed to do so because node list is a friend of iterator. Okay, yeah. So here they return the size, check if it's empty, check if it's 0. Okay, so in the constructor they created nodes for head and tail, right? And then they set next to head, and then previous trailers, previous is they point it to the new node, right? They are both empty. The beginning, they're gonna return an iterator of passing in the heads next. And then here they're passing in iterator of trailer. So what does that mean? Well, they had a where's the iterator class? Okay, so the iterator class had the operators star, equal, not equal, and plus, minus, right? So because of this, all these things, they want to use all these things, right? So that's why they have an iterator. They return an iterator. Because the node, each one is an iterator, right? iterator. So this function, node list begin, returns an iterator. So they return an iterator and they pass the next value. Because headers initial one is the begin is the first value is the one after head. How they define it here, right? They're defining head as, which is kind of crazy here, but they're defining head. This is head, right? Head. They're defining head, tail. So this only has one element. The head is gonna, head's next is gonna be the first value. So here when they do begin, they're passing head's next, which is this, 1. It's kind of crazy, but yeah, that's how they're making it. And they're passing in the tail, which is here. And that makes sense. Why? Because we're returning iterator of n. Because they said that end beginning, it was pointing to like an imaginary thing, right? So I don't know if it was one of the things here. Wait, oh yeah, end was pointing to something something after the last element. So here, that's the reason why they return the trailer, because it's an imaginary thing after the last element. Considering 1 is the only element here, so one's first and last technically. Yeah. So yeah, that's why they end the tail, which is the trailer. That's why end returns the trailer, because it's imaginary after the last element. That's why. Yeah. Next, you're going to see how to implement the insertion. There are 3 different public insertion functions: insert, insert front, insert back, which are shown in the code. The function insert performs insertion into the doubly linked list using the same approach that was explained in section 3.3. In particular, let W be a pointer be P's node and let U be a pointer to P's predecessor. We create a new node and link it to W and P, and increment n to indicate that another link is added. Okay, so yeah, this is the same thing how you inserted nodes before. Just insert, create a new node, insert it between it, and then have them point to each other. I'm not going over that because we already went over how it works. Inserting in front, just call insert at begin, call insert at the end. Yeah. Finally, we present the implementation of the erase function, which removes a node from the list. Again, our approach follows directly from the method described earlier for removing a node from a doubly linked list. Let V be appointed to the node to be deleted, and let W be its successor and U be its predecessor. We unlink V by linking U and W to each other. Once V has been unlinked from the list, we need to return its allocated storage in the system in order to avoid many memory leaks. So then you decrement none of it. Okay. So yeah, there are a number of other enhancements that could be added to our implementation of the node list, such as better error checking, a more sophisticated suite of constructors, and a post increment operator for the iterator class. You might be wondering why we choose to define the iterator end to return an imaginary position that just relies on the end of the list rather than the last node. This choice has advantages. First, it is well defined even if the list is empty. Second, the function insert can be used to insert a new element at any position of the list. In particular, it is possible to insert an element at the end of the list by invoking insert end E. If we had instead defined end to return the last position of the list, this would not be possible. And the only way to insert an element at the end of the list would be through insert back function. Observe that our implementation is quite efficient with respect to both time and space. All of the operations of list ADT run in O of 1 time. The only exceptions to this are omitted housekeeping functions, the destructor, constructor, and assignment operator. They require O of n time, where n is the number of elements in the list. The space used by the data structure is proportional to the number of elements in the list. Okay. STL lists. Okay, so I'm gonna get a drink of water again. Good water's good hydration. So we talked about how to implement lists and just how to create our own lists. But let's talk about this C++ library of their list, which is way more useful because, I mean, why reinvent the wheel when you could just use theirs, right? So here are STL's lists. So to define an object of type list, you have to include in the system's files first, which is simply called list. As with the STL vector List class is a member of the std namespace. It is necessary to either to preface references to it with the namespace resolution operator as an std list or to provide an appropriate using statement. The list class is templated with the base type of the individual elements. For example, the code fragment below declares a list of floats. By default, the initial list is empty. This creates a list of floats. Below is this list of the principal member functions of the list class. Let L be declared to be an STL list of some base type, and let X denote a simple object of this base type. So, yeah, this just makes the list with n elements. This is like declaring an array of how the size of you want it to have n elements. Size returns the number of elements in L. Empty returns true if L is empty and false otherwise. Front returns a reference to the first element of L. Back returns a reference to the last element of L. Push front inserts a copy of E at the beginning of L. Push back inserts a copy of E at the end of L. Pop front removes the first element of L. Pop back removes the last element of L. The functions push front and push back are the STL's equivalents of our functions insert front and insert back of our list ATD. Similarly, the functions pop front and pop back are equivalent to the respective functions erase front and erase back. Note that when the base type of an STL vector is class object, all copying of elements is performed by invoking the base class's copy constructor. Whenever elements are destroyed, for example by invoking the destructor or the pop back member function, the class's destructor is invoked on each deleted element. Alright, let's talk about containers and iterators. Okay, so in order to develop a full understanding of STL vectors and lists, is necessary to understand the concepts of containers and iterators. Recall that a container is a data structure that stores a collection of elements. STL provides a variety of different container classes. We have vector, DQ, double-ended queue, list, stack, queue, priority queue. Priority queue, we'll go over that. Set, multi-set, we'll go over that. Map, we'll go over that. I told you how maps work in the other lecture, in the exercise. The different containers organize their elements in different ways and hence support different methods for accessing individual elements. STL iterators provide a relatively uniform method for accessing and enumerating elements stored in containers. Before introducing how iterators work for STL containers, let us begin with a simple function that sums the elements of a vector. We already done this before. It just loops through it, sums them all up at each index I, and then returns sum. Alright, this is a function that sums up all the elements of STL vector. This particular method of iterating through the elements of a vector should be quite familiar now. Unfortunately, this method will not be applicable to other types of containers because it relies on the fact that elements of a vector can be accessed efficiently through indexing. This is not true for all containers. You can't index everything at a specific index, which is why we desire is a uniform mechanism for accessing elements. So let's talk about iterators. Well, every STL container class defines a special associated class called an iterator, and as mentioned earlier, an iterator is an object that specifies a position within a container and is endowed with the ability to navigate to other positions. If P is an iterator that refers to some position within a container, then star P yields a reference to the associated element. Advancing to the next element of the container is done by incrementing the iterator. For example, either ++P or P++ advances P to the next element of the container. The former returns the updated value of the iterator, and the latter returns to its original value. Each STL container class provides two member functions beginning and end, each of which returns an iterator for this container. The first returns an iterator that points to the first element of the container, and the second returns an iterator that can be thought of as pointing to an imaginary element just beyond the last element of the container. Okay, n always points to the imaginary at the end of the container. Okay, so let us first see how we can use iterators to enumerate the elements of a STL container. So for example, suppose that C is a type vector and that it is an STL list of integers. The associated iterator type is denoted as vector iterator. In general, if C is an STL iterator container of some type cont, the base type is type base, then the iterator would be denoted as cont base iterator. That's just saying the type. So here's how you sum up the elements using an iterator. You create an iterator called P, whatever it is. Have a point to v.begin. That's the begin of it, okay? So that's how you start the loop, right? That points to the first element of the thing. Then you set while it's not equal to the end, you add it. You pre-decrement though. So you add that first. You add it first. You don't post decrement, because if you post decrement, well, someone's gonna have a problem when it hits the end, because at the end points to the imaginary one just at the end. It doesn't point to the last element. It points to one after the last element. So that's where we pre-decrement. Controlled by the iterator P, we start at beginning and terminate when P reaches end. Although this is less direct than the base approach of indexing, it has an advantage that can be applied to any STL container class, not just vectors. Different containers provide iterators with different capabilities. Most STL containers, lists, sets, and maps provide the ability to move not only forwards but backwards as well. For such containers, a decrement operator and post-decrement are defined for the iterators. Is called bidirectional iterator. A few STL containers support the additional feature allowing the addition to subtract of an integer. For example, for an iterator, P plus 3 represents the 3 positions after P of the container. This is called random access iterator. Yeah, okay. Two sides of pointers. Care is in use of iterators. For example, it's up to the programmer to be sure that an iterator points to a valid element of the container before attempting to dereference it. Attempting to dereference an invalid iterator can result in your program aborting. As mentioned earlier, iterators can be invalid for various reasons. For example, an iterator becomes invalid if the position that it refers to is deleted. Okay, const iterators. Observe that we pass the vector v into the function by value. This could be quite inefficient because the system constructs a complete copy of the actual element, right? Since our function does not modify v, the best approach would be to declare that to be const reference. Yeah, I do this a lot. I always do make const reference. Problem arises, however, you declare iterator for a vector. Many STL implementations generate an error if you attempt to use a regular iterator with a const reference. Oh, I didn't know that. Since an iterator may lead to an attempt to modify the vector's contents. The solution is a special read-only iterator called const iterator. Oh, that's cool. When using a const iterator, it is possible to read the values of the container by dereferencing the iterator, but it's not possible to modify the container's values. For example, if P is a const iterator, it's possible to read the value of star P, but you cannot assign it to a value. Oh, so it's only read-only. Okay. The const iterator type for our vector type is denoted as vector int const iterator. We can make use of the type def to rename this lengthy definition to a more concise const iterator. Oh, that's really cool. Okay. So the reason why we do this is because we don't want to make copies of the vector every time, and you can't create an iterator to a const, because that would be impossible. You have to add, because it means you can't modify the pointer. That's why they have something called const iterators. That's the reason why. Okay, STL-based container functions. Okay, so STL offers a flexible, uniform access to the elements of STL containers. Many of the member functions are predefined algorithms that work with STL containers use iterators as their assigned arguments. Here are a few of the member functions of the STL vector class that use iterators as arguments. Let v be an STL vector of some given base type, and let e be a object of this base type. Let p and q be iterators over this base type, and both drawn from the same container. Vector PQ constructs a vector by iterating between P and Q, copying each of these elements into a new vector. Assign PQ deletes the contents of V and assigns it its new contents by iterating between P and Q and copying each of the elements into V. Insert inserts a copy of each just prior to the position given by the iterator, and P and shifts the subsequent elements one position to the right. Erase, removes, and destroys the element of V at the position Q by shifting them one position to the left. Erase P and Q iterates between P and Q, destroying all elements between these are... Why? Okay. Iterate between P and Q destroys all elements between P and Q. Why? Clear deletes all elements of V. Okay. Yeah, these are just crazy functions. Yeah. These are very crazy functions. Okay. When presenting a range of iterator values, assign and erase, the iterator range is understood to start with P and N just prior to Q. Borrowing from interval notation in math, you're starting with P, but you're not including Q. Okay, yeah. That makes sense because Q points to an imaginary end. That's why. So you're not including the imaginary end. If that makes any sense. Like, Q points to an imaginary end here. So if I want to include all elements from, like, P to Q, I'm not going to include Q. I'm going to include P and then go up to here and not include Q. That's my Q. Because it points to an imaginary end. Note that the vector function insert and delete moves elements around the vector. We should use them with care because they could be slow. For example, inserting or erasing an element at the beginning of a vector causes all the later elements of the vector to be shifted in one position. The above functions are also defined for the STL list and STL DQ. Of course, the constructors are named differently. Since the list is defined as a doubly linked list, there is no need to shift elements when performing insert or erase. These three STL containers, vector, list, DQ, are called sequence containers because they explicitly store elements in sequential order. The STL containers set, multi-set, map, multi-map support all of the above functions except assign. They are called associated containers because elements are typically accessed by providing a key value. Okay. Yeah. It's worthwhile note that in a constructor and destructor, constructor and assignment, my bad. The iterators P and Q do not need to be drawn from the same type as Q, as long as the container they are drawn from has the same base type. For example, suppose that L is an STL list container of integers. We can create a copy of L in a form of STL vector. Okay, yeah. So if you create a copy of L, just create V, and then you pass in these iterators begin and end, and that creates a copy of L. Iterator-based form of the constructor is quite handy since it provides an easy way to initialize the contents of an STL container from a standard C++ array. Here we make use of a low-level feature C++ inherited from C. Recall that we express a pointer to its first element of A at 0, A plus 1 points to A1, A plus 2 points to A2, A plus I points to AI. Yeah, we know that. This is called pointer arithmetic. Is found in programming practice, but in this instance it provides an elegant way of doing it. Okay, so start from A plus 5, 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. Okay, so this is the imaginary end. That's why it points to the imaginary end. That's why you could include this. Okay, it's magic of pointer arithmetic. Okay. It's frowned upon, though. Here are some more methods in vectors and algorithms. In addition to the above member functions of STL vectors, STL also provide a number of algorithms that operate on containers in general, vectors in particular. To access these functions, use the include statement include algorithm. Let P and Q be iterators over some base type. Let E denote an object of this base type. As above, these operations apply to the iterator range P up to Q, not including Q. Sort PQ sorts the elements from P to Q to ascending. Random shuffle randomly shuffles these elements. Reverses the order. Find returns the iterator first in the range from P to Q that is equal to E. If E is not found, Q is returned. Returns the iterator from P to Q that is equal to E. Oh, okay. So what does this mean? It searches the elements from beginning to end. Anything that's equal to E, and then if it's found, it returns whatever position it was. That's what this means. Min element returns the minimum element. Oh, I would use this a lot. Okay, I should do that. Max element returns max. Ooh. Okay, for each applies a function that goes to P and Q and applies a function. That's amazing. Okay, I'm gonna use these actually. I'm gonna use the min, element, max, and find. Maybe for each also. For example, to sort, you use sort beginning to the end. You want to sort the first 10, do sort beginning plus 10. All above functions are supported for the STL DQ. All above functions except sort and random shuffle are supported in list. Okay, remember to include algorithm and vector. Okay. We first initialize a standard C++ array containing 6 integers, and we use them, the iterator-based constructor, to create a 6-element vector containing these values. We show how to use the member function size, pop, push, back, front. Observe that popping decreases the array size, pushing increases array size. We then show how to use an iterator arithmetic to sort a position of the vector, in this case the first 4 elements. The call of the arrays function removes first the last two of the last 4 elements. Okay. After removal, the remaining 2 elements of the end has been shifted to fill empty positions. Next, we demonstrate how to generate a vector of characters. We apply the function random shuffle to permute the elements of the vector randomly. Finally, we show how to use the member function insert to insert a character at the beginning of the vector. Observe how all the other elements are inserted from the beginning. Okay, yeah, so they're just testing all these functions. Alright, let's talk about sequences. Alright guys, it's late at night, but I'm going to finish this video by talking about sequences and then bubble sort. Alright, so what are sequences? See, we define a sequence that generalizes the vector list and ADTs. The abstract data type provides access to its elements, both indices and positions, and is a versatile data structure for a wide range of applications. Well, a sequence in an ATD that supports all the functions of the list, but also provides functions for accessing elements by the index. And we did this for the vector. Interface consists of the operations of the list ADT plus the 2 bridging functions that provide connections between indices and positions. At index returns the position of the element at index I. Index of P returns the index of the element at position P. So you could implement a sequence with a doubly linked list. One implementation of a sequence is with a doubly linked list. You use all the same functions of the list. Can easily run in O of 1 time. Functions at index and index of the vector can also be implemented with a doubly linked list, though in a less efficient manner. In particular, if you want the functions from the list to run efficiently, using positions objects to indicate which access and updates should occur, then we can no longer explicitly store the indices of elements in the sequence. Hence, to perform the operation at index, we must perform a link hopping to the end until we can locate the node stored at the index I. For a slight modification and optimization, we could start hopping from the closest end of the sequence, which could be achieved by the running time O of min I plus 1 and minus 1. This is still O of n is in the worst case, but it would be more efficient in applications where many calls at index I are expected to involve index values that are significantly closer to either end of the list. In our implementation, we can just use a simple approach of walking from the front of the list. We can leave the two-sided solution as an exercise. In code fragment 6.117, we present a definition of a class node sequence, which implements the sequence ADT. Observe that because the sequence extends the definition of a list, we have inherited our class by extending the node list class. That was introduced in section 6.2. We simply add definitions of our bridging functions. Through the magic of inheritance, the users of our class node sequence have access to all the members of the node list class, including its nested class, node list iterator. Okay, yeah. So now you have all the functions of node list because of inheritance. And now you have at index, which returns a position from index, and you could get an index from position using index of. Then the definition of a class node sequence, which implements the sequence ADT using a doubly linked list. Next, in code fragment 6.18, we show that the implementation of the at index and index of member functions. The function at index hops I in positions to the right, starting from the beginning, and returns the resulting position. The function index of hops through the list until finding the position that matches the given position P. Observe that the conditional Q not equal P uses overloaded comparison operator for positions defined in code fragment 6.8. Okay, so at position returns the iterator from this position at this index. Index of returns the position of the index. Yeah. So at the position of the index. Yeah. They do this by looping through it until they get it. Okay. Both of these functions are quite fragile. likely to abort if the argument are not in bounds. A more careful implementation of index would be to check that the index I lies in the range from 0 to n minus 1, where n is the size of the sequence. The function index of should check that it does not pass the end of the sequence. In either case, the appropriate exception should be thrown. Worst case running time of both functions at index and index of are O of n, where n is the size of the list. Although this is not efficient, we may take consolation in the fact that all other operations of the list ADT run in time O of 1. A natural alternative approach would be to implement the sequence ADT using an array. Although we could provide very efficient implementations of at index and index of, the insertion and removal operations of the list ADT would now require O of n time. Thus, neither solution is perfect under all circumstances. We explore this alternatives in the next section. Okay, so implementing a sequence with an array. We could implement a sequence by storing each element in an array. We could define a position p to hold the index I in reference to a as member variables. We can then implement functions p by returning the reference. Major drawback here is that the solves in A have no reference to their corresponding positions. For example, after performing an insert front option, the elements should be shifted to a new position, but we have no way of informing the existing position of S for that associated positions of the elements have changed. Hence, if we're going to implement a general sequence with an array, we need to find a different approach. Consider an alternative solution. Instead of storing the elements of S into an array, we store a pointer to a new kind of position object in each position of A. Each position object P stores a pair consisting the index I and the element E associated with P. We can easily scan through the array to update the value I associated with each position whose rank changes as a result of an insertion or deletion. Example is shown in 6.7, where a new element containing BWI is inserted at index 1 of an existing sequence. After the insertion, the elements PVD and SFO are shifted to the right, so we increment the index value associated with the index element pair. Okay, so this time they have a pair for every single value at the index. So when you add a new position, let's say you add 3 here, you just shift everything to the right, add the index to the right. And what about decrementing? That's what I'm curious. So like when they add a new position here, this now just becomes whatever the new position was added. Right, and then everything gets shifted to the right, so you just change the pointer to point to whatever is right, and that allows you to have the index associated with it. Okay, in the array-based implementation of a sequence, the function insert erase take O of n time because we have to shift position objects to make room for the new position or to fill in the hole created by the removal of the old position. All the other position-based functions take O of 1 time. Note that we can use an array in a circular fashion as we did for implementing a queue. With little work, we can then perform functions insert front at O of 1 time. Note that functions insert and erase still take O of n time. Now the worst case scenario occurs when we need insert and remove has rank n over 2. Okay. Comparing the running times of size empty over 1 over 1. O index of takes O of n for a list. Begin n takes O of 1. Okay, referencing. Insert erase for circular array takes O of n. For list takes O of 1. Okay, comparing each of the running times of sequence needed for it either with an array or doubly linked list, we denote with n the number of elements in this sequence at the time the operation is performed. The space usage is O of n. O of n for the doubly linked list implementation, O of n for the array implementation, where n is the size of the array. Summarizing this table, we see that the array-based implementation is superior to the linked list implementation on the rank-based access operations at index and index of. It is equal in performance to the linked list implementation on all of the other access operations. Regarding update operations, the linked list implementation beats the array implementation in the front, back, and operation insert and delete. For the update operations, insert front and insert back, the two implementations have comparable performance. So considering space usage, note that an array requires O of n space, where n is the size of an array, while a doubly linked list considers O of n, where n is the number of elements in the sequence. Since n is less than or equal to n, This implies that the asymptotic space usage of a linked list implementation is superior to that of a fixed size array, although there is a simple small factor overhead that is larger for linked lists, since arrays do not need links to maintain the order of the cells. Alright, let's talk about bubble sort. Okay, so basically how would you normally do a bubble sort? Well, okay, basically bubble sort is like, okay, this is really an inefficient algorithm, but it's like a baby doing sorting, right? How would a baby doing sorting? It would just compare whatever was on the next value. So if I have 5, 2, and 3, if I want to make a bubble sort, I'll just compare whatever's next to it. Then I was like, okay, is this 2 less than 5? Yes, it is. I'll have to swap it, right? Then I start here, and I got to compare 5 and 3. And I was like, is this sorted? Well, it's 5 and less than 3. I got to swap it. So after 2, 3, 5. Then I got to compare 3 and 2. Is it less? Well, no, it stays there. That's what a bubble sort technically is, okay? Consider a sequence of n elements such as any 2 elements of the sequence can be compared according to the order relation, okay? A sorting problem is to reorder the sequence so the elements are in non-decreasing order. The bubble sort solves this problem by performing passes over the sequence. Each pass, the elements are scanned by increasing rank from 0 to the end of the sequence. At each position in the pass, an element is compared with its neighbor, and if these 2 elements can be found in the wrong relative order, you swap them. The sequence is sorted by completing n such passes. So if I want to swap 5, 7, 2, 6, 9, 3, compare 5 and 7, right? And then if it is 7 greater than 5, no, okay? Now compare 7 and 2. Is 2 greater than 7? Yeah, so then they swap 2 and 7, right? Then they check if 6 is greater than 7, right? Because after they swap 2 and 7, and then they swap that with, so you get 2, 6, and 7. Then you check if is 9 greater than 3. Yeah, they swap 3 and 9. So that's what this whole swap was about. 7 and 2 was swapped. 6 and 7 was swapped. 9 and 3 were swapped. Okay, so that's why you get this whole thing. Then they gotta do it again. All right, you check 2 and 5. Is it swapped? Yeah, swap it. Check 6 and 5. Yeah, okay, it's in order. Okay, check 6 and 3. No, they don't check 6 and 3. They check 3 and 7. Is 3 and 7 fine? Okay. No, yeah, they do. They check 6 and 3 and then swap it. And then 7, 9. And then they go check 5 and 3. Okay, so then after that, you gotta check it again. Check is 5 greater than 3 to swap it. Okay, wow. The insertions, did I say insertion sort? My God. Bubble sort algorithm on a sequence of integers. For each pass, the swaps are performed in the sequence after the pass are shown. Bubble sort algorithm has the following properties. In the first pass, once the largest element is reached, it keeps on being swapped until it gets the last element of the sequence. In the second pass, once the second to last largest element is reached, it keeps on being swapped until it gets to the second to last position of the sequence. In general, at the end of the ith pass, the rightmost I elements of the sequence, that is, those at indices from n-1 down to n-I, are in the final position. The last property implies that it is correct to limit the number of passes made by a bubble sort on an n-element sequence to n. Moreover, it allows us to make the ith pass to be limited to the first n-1 plus 1 elements of the sequence. So here's an analysis of a bubble sort. We assume that the implementation of the sequence is such that the access to elements and the swap of elements performed by bubble sort takes O of 1 time, as running time of the ith pass is O of n-1 plus 1. We have the overall running time of bubble sort as this. We can rewrite the sum of the big O notation as this. By proposition, we have this. Okay. Thus, bubble sort runs in O of n squared time, provided that access and swaps can each be implemented O of 1 time. As we have seen future chapters, this performance is quite inefficient. We discuss bubble sort here. Our aim is to demonstrate not as a good example of a good sorting problem. This presents 2 implementations of bubble sort on a sequence of integers. Parameter S is of type sequence, but we do not specify whether it is a node-based or array-based implementation. The 2 bubble sort implementations differ in the preferred choice of functions to access and modify the sequence. The first is based on accessing elements by their index. We use the function addIndex to access the two elements of interest. Since function bubble sort 1 accesses elements only through the index-based interface functions addIndex, this implementation is suited only for the array-based implementation of the sequence, for which addIndex takes O of 1 time. Given such an array-based sequence, this bubble sort implementation runs O of n squared time. On the other hand, if we had used our node-based model, it would take O of n time as the worst case, since this function is called with each iteration of the inner loop. The entire function would run O of n third time. Oh my god, which is slow if n is large. In contrast to bubble sort 1, our second bubble sort 2 accesses the element through iterators. The iterators pre and sync play roles such as j-1 and j play respectively in bubble sort 1. Observe that when we first enter the first loop of bubble sort, the value of j-i is 0, which refers to the first element of the sequence is y correct in the beginning. Okay, so bubble sort 1, we're going to use a predecessor and to swap them. Okay, this is based on indices of a sequence before entering the inner loop. Whenever we re-enter the inner loop, we initialize suck to prec and immediately increment it. Okay, so they're using iterators to get the predecessor and successor of each swap, so then they could swap it. Before presuming the loop, they pre-increment prec. Okay, so now they have the better version, which is to have the iterator point to the beginning, and they're going to loop through to the one after I, right? And then they're going to have the successor point to the predecessor and add it. And then they swap if it's out of order. Okay, so since the iterator incremented takes O of 1 time, either the array-based or node-based implementation of the sequence, this implementation of bubble sort will run O of n squared worst case time, irrespective of the manner in which the sequence was implemented. The two bubble sort implementations given above show the importance of providing efficient implementations of ADT. Nevertheless, in spite of its implementation, good researchers have found that bubble sort is not a good sorting algorithm. Even if it is implemented in the best possible way, it takes quadratic time. Indeed, there are more efficient sorting algorithms that run in O of n log n time. And that was it, okay? Please rate, comment, subscribe. I'll check you guys later. I'm really tired. That was all of lists and iterators and sequences. List, iterators, ADTs. Tomorrow we're gonna go over trees. Rate, comment, subscribe.